Hello everyone, I'm Zhang Faxiu from Sichuan University. Today I will present our work on mechanical properties, degradation of carbon glass hybrid composites, and hygrosmal condition. First, let me outline the structure of my presentation. I've organized my talk into five main parts. Let me begin with the research background. Composite materials are widely used in the aerospace and wind energy sectors due to their excellent properties. However, in practice, they often face harsh environments such as high temperature and high humidity. This can lead to the decline in mechanical performance of the structure, threaten safety and service life. Although there is currently a lot of research, most studies focus on either moisture diffusing or mechanical property degradation, with a lack of complement between them. The current body of research on the mechanical property degradation of hybrid fiber composites and hygrosmal agent exhibit numerous shortcomings. So, how did we do it? We combine the experiments and the simulation. Experiments gave us real-world data on water uptake and stress loss. Then, we built compute model that link the water diffusing directly to the mechanical failure, and we check if our model's prediction match our experiments. Let me first introduce the experiment work. We made two types of laminates with the same layout sequences, 0, 19, and 45. We chose them because they fail in very different ways. The 19 laminate is strong and fail due to their fiber breakage, where the 45 laminate is tougher and fail more due to mixture and interface shear. To accelerate the agent, we put our samples in hot water at 19 degrees. We wet them regularly until they stopped absorbing water, which we called saturation. Tensor tests were conducted before agent began, and then repeated every 6 days until saturation. Meanwhile, we also use SCM to observe the fracture surface at key intervals before aging, and then every 12 days to direct link the mechanical property change to physical damage mechanics. Now let me turn to our modeling work. We built a model for water diffusing based on fixed law. The element type is DC3D8. The core of our modeling is a damage simulation. This is our main innovation. A viewmat subroutine implementing a progressive damage model. It incorporates several key features. It accounts for hygrosmal agent effects, use Hessian's criticals for damage innovation, and model damage evolution based on feature energy. Essentially, it translates moisture diffusing into mechanical property degradation and predicts subsequent failure procedure. Now let's look at what we found. The results of the moisture absorption test, simulation, and numerical fitting are shown in the figure. We can observe that moisture absorption is fakers and unaffected by the layup, with both laminate saturating at 1.17% after 36 days. The excellent match between simulation and experiment confirms our model is reliable. The simulation provides deeper insights. It confirms that layup has no effect on final outcome. Water models diffusing from the surface to the interior, but also uncovered the internal process, a significantly higher diffusion rate in the GFRP layers. Now, let's see how this affects failure. The Lanxin laminate is inhibited brittle fracture dominated by fiber tensile failure with a relatively flat surface. After aging, its fracture surface becomes rougher. In contrast, the 45 laminate demonstrated significant shear dominated failure exhibited irregularly, swallow-tailed fracture. After aging, we see more delamination. This different failure lead to different mechanical loss. The 19 laminate lost 37% of its strength, and the 45 laminate lost 24% of its strength, but its stiffness dropped by the 30%. This tells us the mixture and the interface, which control the behavior of the 45 laminates, are more sensitive to water. Now, the critical question, can our model predict this? The answer is yes. For both laminates, simulations show excellent agreement with experiment. Load displacement curves. This validates our modeling ability to predict mechanical response after high-gradient agent. Now let's analyze the stress distribution from our simulation. For the Lanxin laminate, we see a relatively regular fracture pattern. As agent time increases, the overall stress level decreases. If we look closer, the CFRP layers carry most of the loads, as their stress is close to the overall value. In contrast, the GFRP layers show much lower stress, indicating they are weaker and contribute less to the loader bearing capacity after. Now, for the 45 laminates, unlike the flat fracture of the 19, it shows irregularly. However, the stress distribution reveals a similar story. The CFRP layers still bear the major of load. Finally, the SCM image shows us why. For the 19 laminates, aging causes more fiber debonding, and you can see less resin sticking to the pour-out fiber. For the 45 laminates, the main problem are worsening delamination between layers and damage at the fiber mixture interface. This directly evidence of why the 45 laminates suffered such a large stiffness loss. This is my conclusion. That brings me to the end of my presentation. Thank you for your attention.